design of his system. The data entities in the data mind map in Figure 2.8. The code modules in the module diagram in Figure 2.9. A bit perplexed, Theo asks Joe, "Theo, I'm not sure that this system is better than a traditional OOP system where objects encapsulate data." Joe, "The main benefit of a DOP system over a traditional OOP system is that it's easier to understand." Theo, "What makes it easier to understand?" Joe, "The fact that the system is split cleanly into code modules and data entities." Theo, "How does that help?" Joe, "When you try to understand the data entities of the system, you don't have to think about the details of the code that manipulates the data entities." Theo, "So when I look at the data mind map of my library management system, I can understand it on its own?" Joe, "Exactly. And similarly, when you try to understand the code modules of the system, you don't have to think about the details of the data entities manipulated by the code. There is a clear separation of concerns between the code and the data." Theo looks again at the data mind map in Figure 2.8. He has kind of an aha moment. Data lives on its own. Note: a DOP system is easier to understand because the system is split into two parts, data entities and code modules. Now, Theo looks at the module diagram in Figure 2.9. He feels a bit confused and asks Joe for clarification. On one hand, the module diagram looks similar to the class diagrams from classic OOP, boxes for classes and arrows for relations between classes. On the other hand, the code module diagram looks much simpler than the class diagrams from classic OOP, but he cannot explain why. Theo, "The module diagram seems much simpler than the class diagrams I'm used to in OOP. I feel it, but I can't put it into words." Joe, "The reason is that module diagrams have constraints." Theo, "What kind of constraints?" Joe, "Constraints on the functions we saw before. All the functions are static or stateless, but there's also constraints on the relations between the modules." Tip: all the functions in a DOP module are stateless. Theo, "In what way are the relations between modules constrained?" Joe, "There is a single kind of relation between DOP modules, the usage relation. A module uses code from another module. There's no association, no composition, and no inheritance between modules. That's what makes a DOP module diagram easy to understand." Theo, "I understand why there is no association and no composition between DOP modules. After all, association and composition are data relations. But why no inheritance relation? Does that mean that DOP is against polymorphism?" Joe, "That's a great question. The quick answer is that in DOP, we achieve polymorphism with a different mechanism than class inheritance. We will talk about it someday." Note: for a discussion of polymorphism in DOP, see Chapter 13. Theo, "Now you've piqued my curiosity. I thought inheritance was the only way to achieve polymorphism." Theo looks again at the module diagram in Figure 2.9. Now he not only feels that this diagram is simpler than traditional OOP class diagrams, he understands why it's simpler. All the functions are static, and all the relations between modules are of type usage. Table 2.1 summarizes Theo's perception. Tip: the only kind of relation between DOP modules is the usage relation. Tip: each part of a DOP system is easy to understand because it provides constraints. Section 2.5. DOP systems are flexible. Theo, I see how a sharp separation between code and data makes DOP systems easier to understand than classic OOP systems. But what about adapting to changes in requirements? Joe, another benefit of DOP systems is that it is easy to extend them and to adapt to changing requirements. Theo, I remember that when Nancy asked me to add super members and VIP members to the system, It was hard to adapt my OOP system. I had to introduce a few base classes, and the class hierarchy became really complex. Joe, I know exactly what you mean. I've experienced the same kind of struggle so many times. Describe the changes in the requirements for super members and VIP members, and I'm quite sure that you'll see how easy it would be to extend your DOP system. The requirements for super members and VIP members. Super members are members that are allowed to list the book lendings to other members. VIP members are members that are allowed to add book items to the library. Theo opens his IDE and starts to code the getBookLendings function of the library module. See listing 2.3. First, without addressing the requirements for super members. Theo remembers what Joe told him about module functions in DOP. Functions are stateless. Functions receive the data they manipulate as their first argument. In terms of functionality, getBookLendings has two parts. Checks that the user is a librarian, retrieves the book lendings from the catalog. Basically, the code of getBookLendings has two parts as well. Calls the isLibrarian function from the user management module and passes it the user management data. Calls the getBookLendings function from the catalog module and passes it the catalog data. It's Theo's first piece of DOP code, and passing around all those data objects, library data, librarydata.usermanagement, and librarydata.catalog, feels a bit awkward. But he did it. Joe looks at Theo's code and seems satisfied. Joe, now how would you adapt your code to super members? Theo, I would add a function isSuperMember to the user management module and call it from library.getBookLendings. Joe, exactly. It's as simple as that. Theo types the code on his laptop so that he can show it to Joe. Here's how Theo adapts his code for super members. Now, the awkward feeling caused by passing around all those data objects is dominated by a feeling of relief. Adapting to this change in requirements takes only a few lines of code and requires no changes in the system design. Once again, Joe seems satisfied. Tip: DOP systems are flexible. Quite often, they adapt to changing requirements without changing the system design. Theo starts coding addBookItem. He looks at the signature of library.addBookItem, and the meaning of the third argument, bookItemInfo, isn't clear to him. He asks Joe for clarification. Theo, what is bookItemInfo? Joe, let's call it the book item information. Imagine we have a way to represent this information in a data entity named bookItemInfo. Theo, you mean an object? Joe, for now, it's okay to think about bookItemInfo as an object. Later on, I will show you how we represent data in DOP. Besides this subtlety about how the book item information is represented by bookItemInfo, the code for library.addBookItem in listing 2.6 is quite similar to the code Theo wrote for library.getBookLendings in listing 2.4. Once again, Theo is amazed by the fact that adding support for VIP members requires no design change. Theo, it takes a big mindset shift to learn how to separate code from data. Joe, what was the most challenging thing to accept? Theo, the fact that data is not encapsulated in objects. Joe, it was the same for me when I switched from OOP to DOP. Now it's time to eat. Theo takes Joe for lunch at Simple, a nice, small restaurant near the office. Summary: DOP principles are language-agnostic. DOP principle number 1 is to separate code from data. The separation between code and data in DOP systems makes them simpler, easier to understand, than traditional OOP systems. Data entities are the parts of your system that hold information. DOP is against data encapsulation. The more flexible a system is, the easier it is to adapt to changing requirements. The separation between code and data in DOP systems makes them more flexible than traditional OOP systems. When code is separated from data, we have the freedom to design code and data in isolation. We represent data as data entities. We discover the data entities of our system and sort them into high-level groups, either as a nested list or as a mind map. A DOP system is easier to understand than a traditional OOP system because the system is split into two parts, data entities and code modules. In DOP, a code module is an aggregation of stateless functions. DOP systems are flexible. Quite often they adapt to changing requirements without changing the system design. In traditional OOP, the state of the object is an implicit argument to the methods of the object. Stateless functions receive data they manipulate as an explicit argument. The high-level modules of a DOP system correspond to high-level data entities. The only kind of relation between code modules is the usage relation. The only kinds of relation between data entities are the association and the composition relation. For a discussion on polymorphism in DOP, see Chapter 13. Chapter 3. Basic Data Manipulation. Meditation and Programming. This chapter covers representing records with string maps to improve flexibility, manipulating data with generic functions, accessing each piece of information via its information path, gaining JSON serialization for free. After learning why and how to separate code from data in the previous chapter, let's talk about data on its own. In contrast to traditional OOP, where system design tends to involve a rigid class hierarchy, DOP prescribes that we represent our data model as a flexible combination of maps and arrays, or lists, where we can access each piece of information via an information path. This chapter is a deep dive into the second principle of DOP. Principle number 2. Represent data entities with generic data structures. We increase system flexibility when we represent records as string maps and not as objects instantiated from classes. This liberates data from the rigidity of a class-based system. Data becomes a first-class citizen powered by generic functions to add, remove, or rename fields. Note: we refer to maps that have strings as keys as string maps. The dependency between the code that manipulates data and the data is a weak dependency. The code only needs to know the keys of specific fields in the record it wants to manipulate. The code doesn't even need to know about all the keys in the record, only the ones relevant to it. In this chapter, we'll deal only with data query. We'll discuss managing changes in system state in the next chapter. Section 3.1. Designing a Data Model. During lunch at Simple, Theo and Joe don't talk about programming. Instead, they start getting to know each other on a personal level. Theo discovers that Joe is married to Kay, who has just opened her creative therapy practice after many years of studying various fields related to well-being. Nariah, their 14-year-old son, is passionate about drones, whereas Aurelia, their 12-year-old daughter, plays the transverse flute. Joe tells Theo that he's been practicing meditation for 10 years. Meditation, he says, has taught him how to break away from being continually lost in a storm thought, especially negative thoughts, which can be the source of great suffering, to achieve a more direct relationship with reality. The more he learns to experience reality as it is, the calmer his mind. When he first started to practice meditation, it was sometimes difficult and even weird, but by persevering, he has increased his feeling of well-being with each passing year. When they're back at the office, Joe tells Theo that his next step in their DOP journey will be about data models. This includes data representation. Joe: when we design the data part of our system, we're free to do it in isolation. Theo: what do you mean by isolation? Joe: I mean that you don't have to bother with code, only data. Theo, oh, right. I remember you telling me how that makes a DOP system simpler than OOP. Separation of concerns is a design principle I'm used to in OOP. Joe, indeed. Theo, and when we think about data, the only relations we have to think about are association and composition. Joe, correct. Theo, will the data model design be significantly different than the data model I'm used to designing as an OOP developer? Joe, not so much. Theo, okay. Let me see if I can draw a DOP-style data entity diagram. Theo takes a look at the data mind map that he drew earlier in the morning. He then draws the diagram in Figure 3.1. He refines the details of the fields of each data entity and the kind of relations between entities. Figure 3.2 shows the result of this redefined data entity diagram. Joe, the next step is to be more explicit about the relations between entities. Theo, what do you mean? Joe, for example, in your entity diagram, book and author are connected by a many-to-many association relation. How is this relation going to be represented in your program? Theo, in the book entity, there will be a collection of author IDs, and in the author entity, there will be a collection of book IDs. Joe, sounds good. And what will the book ID be? Theo, the book ISBN. Note: the International Standard Book Number, ISBN, is a numeric commercial book identifier that is intended to be unique. Joe, and where will you hold the index that enables you to retrieve a book from its ISBN? Theo, in the catalog, because the catalog holds a book by ISBN index. Joe, what about author ID? Theo, author ID is the author name in lowercase and with dashes instead of white spaces, assuming that we don't have two authors with the same name. Joe, and I guess that you also hold the author index in the catalog. Theo, exactly. Joe, excellent. You've been 100% explicit about the relation between book and author. I'll ask you to do the same with the other relations of the system. It's quite easy for Theo to do, as he has done that so many times as an OOP developer. Figure 3.3 provides the detailed entity diagram of Theo's system. Note: by positional collection, we mean a collection where the elements are in order, like a list or an array. By index, we mean a collection where the elements are accessible via a key, like a hash map or a dictionary. The catalog entity contains two indexes. Books by ISBN. The keys are book ISBNs, and the values are book entities. Its type is noted as book in braces. Authors by ID. The keys are author IDs, and the values are author entities. Its type is noted as author in braces. Inside a book entity, we have authors, which is a positional collection of author IDs of type string in brackets. Inside an author entity, we have books, which is a collection of book IDs of type string in brackets. Note: for the notation for collections and index types, a positional collection of strings is noted as string in brackets. An index of books is noted as book in braces. In the context of a data model, the index keys are always strings. There is a dashed line between book and author, which means that the relation between book and author is indirect. To access the collection of author entities from a book entity, we'll use the author by ID index defined in the catalog entity. Joe, I like your data entity diagram. Theo, thank you. Joe, can you tell me what the three kinds of data aggregations are in your diagram, and in fact in any data entity diagram? Theo, let's see. We have positional collections like authors in book. We have indexes like books by ISBN in catalog. I can't find the third one. Joe, the third kind of data aggregation is what we've called, until now, an entity, like library, catalog, book, etc., and the common term for entity in computer science is record. Note: a record is a data structure that groups together related data items. It's a collection of fields, possibly of different data types. Theo, is it correct to say that a data entity diagram consists only of records, positional collections, and indexes? Joe, that's correct. Can you make a similar statement about the relations between entities? Theo, the relations in a data entity diagram are either composition, solid line with a full diamond, or association, dashed line with an empty diamond. Both types of relations can be either one-to-one, one-to-many, or many-to-many. Joe, excellent. Tip: a data entity diagram consists of records whose values are either primitives, positional collections, or indexes. The relation between records is either composition or association. Section 3.2. Representing records as maps. So far, we've illustrated the benefits we gain from the separation between code and data at a high system level. There's a separation of concerns between code and data, and each part has clear constraints. Code consists of static functions that receive data as an explicit argument. Data entities are modeled as records, and the relations between records are represented by positional collections and indexes. Now comes the question of the representation of the data. DOP has nothing special to say about collections and indexes. However, it's strongly opinionated about the representation of records. Records should be represented by generic data structures, such as maps. This applies to both OOP and FP languages. In dynamically typed languages like JavaScript, Python, and Ruby, data representation feels natural, while in statically typed languages like Java and C#, it is a bit more cumbersome. Theo, I'm really curious to know how we represent positional collections, indexes, and records in DOP. Joe, let's start with positional collections. DOP has nothing special to say about the representation of collections. They can be linked lists, arrays, vectors, sets, or other collections best suited for the use case. Theo, it's like in OOP. Joe, right. For now, to keep things simple, we'll use arrays to represent positional collections. Theo, what about indexes? Joe, indexes are represented as homogeneous string maps. Theo, what do you mean by a homogeneous map? Joe, I mean that all the values of the map are of the same kind. For example, in a book index, all the values are book, and in an author index, all the values are author, and so forth. Theo, again, it's like in OOP. Note: a homogeneous map is a map where all the values are of the same type. A heterogeneous map is a map where the values are of different types. Joe, now here's the big surprise. In DOP, records are represented as maps, more precisely, heterogeneous string maps. Joe goes to the whiteboard and begins to draw. When he's finished, he shows Theo the diagram in figure 3.4. Theo stays silent for a while. He is shocked to hear that the data entities of a system can be represented as a generic data structure, where the field names and value types are not specified in a class. Then Theo asks Joe, Theo, what are the benefits of this folly? Joe, flexibility and generosity. Theo, could you explain, please? Joe, I'll explain in a moment, but before that, I'd like to show you what an instance of a record in a DOP system looks like. Theo, okay. Joe, let's take as an example Watchmen by Alan Moore and Dave Gibbons, which is my favorite graphic novel. This masterpiece was published in 1987. I'm going to assume that in a physical library there are 2 copies of this book, whose ID is nyc-central-lib, and that one of the 2 copies is currently out. Here's how I'd represent the book record for Watchmen in DOP. Joe comes closer to Theo's laptop. He opens a text editor, not an IDE, and types the book record for Theo. Theo looks at the laptop screen. He has a question. Theo, how am I supposed to instantiate the book record for Watchman programmatically? Joe, it depends on the facilities that your programming language offers to instantiate maps. With dynamic languages like JavaScript, Ruby, or Python, it's straightforward, because we can use literals for maps and arrays. Here, let me show you how. Joe jots down the JavaScript code that creates an instance of a book record, which represents as a map in JavaScript. He shows the code to Theo. Theo, and if I'm in Java? Joe, it's a bit more tedious, but still doable with the immutable map and list static factory methods. Note: see Creating Immutable Lists, Sets, and Maps at this link for more information on this Java core library. Joe types the Java code to create an instance of a book record represented as a map. He shows Theo the Java code. Tip: in DOP, we represent a record as a heterogeneous string map. Theo, I definitely prefer to create a book record using a book class and a book item class. Theo opens his IDE. He types the JavaScript code to represent a book record as an instance of a book class. Joe, Theo, why do you prefer classes over maps for representing records? Theo, it makes the data shape of the record part of my program. As a result, the IDE can autocomplete field names and errors are caught at compile time. Joe, fair enough. Can I show you some drawbacks for this approach? Theo, sure. Joe, imagine that you want to display the information about a book in the context of search results. In that case, instead of author IDs, you want to display author names, and you don't need the book item information. How would you handle that? Theo, I'd create a class book in search results without a book items member and with an author names member instead of the author IDs member of the book class. Also, I would need to write a copy constructor that receives a book object. Joe, in classic OOP, the fact that data is instantiated only via classes brings safety, but this safety comes at the cost of flexibility. Tip: there's a trade-off between flexibility and safety in a data model. Theo, so how can it be different? Joe, in the DOP approach, where records are represented as maps, we don't need to create a class for each variation of the data. We're free to add, remove, and rename record fields dynamically. Our data model is flexible. Theo, interesting. Tip: in DOP, the data model is flexible. We're free to add, remove, and rename record fields dynamically at runtime. Joe, now let me talk about genericity. How would you serialize the content of a book object to JSON? Tip: in DOP, records are manipulated with generic functions. Theo, oh no, I remember that while working on the Clapham prototype, I had a nightmare about JSON serialization when I was developing the first version of the library management system. Joe, well, in DOP, serializing a record to JSON is super easy. Theo, does it require the usage of reflection in order to go over the fields of the record like the JSON Java library does? Note: see github.com/google/JSON for more information on JSON. Joe, not at all. Remember that in DOP, a record is nothing more than data. We can write a generic JSON serialization function that works with any record. It can be a book, an author, a book item, or anything else. Theo, amazing. Tip: in DOP, you get JSON serialization for free. Joe, actually, as I'll show you in a moment, lots of data manipulation stuff can be done using generic functions. Theo, are the generic functions part of the language? Joe, it depends on the functions and on the language. For example, JavaScript provides a JSON serialization function called json.stringify out of the box, but none for omitting multiple keys or for renaming keys. Theo, that's annoying. Joe, not so much. There are third-party libraries that provide data manipulation facilities. A popular data manipulation library in the JavaScript ecosystem is Lodash. Note: see lodash.com to find out more about Lodash. Theo, what about other languages? Joe, Lodash has been ported to Java, C#, Python, and Ruby. Let me bookmark some sites for you. Joe bookmarks these sites for Theo: javaLibs.com/artifact/com.github.javadev/_-lodash for Java. nuget.org/packages/lodash for C#. github.com/dgillen/pydash for Python. rudash-website.now.sh for Ruby. Note: throughout the book, we use Lodash to show how to manipulate data with generic functions, but there is nothing special about Lodash. The exact same approach could be implemented via other data manipulation libraries or custom code. Theo, cool. Joe, actually, Lodash and its rich set of data manipulation functions can be ported to any language. That's why it's so beneficial to represent records as maps. Tip: DOP compromises on data safety to gain flexibility and genericity. At the whiteboard, Joe quickly sketches the trade-offs. See Table 3.1. Section 3.3. Manipulating data with generic functions. Joe, now let me show you how to manipulate data in DOP with generic functions. Theo, yes, I'm quite curious to see how you'll implement the search functionality of the library management system. Joe, okay. First, let's instantiate a catalog record for the catalog data of a library, where we have a single book, Watchmen. Joe instantiates a catalog record according to Theo's data model in Figure 3.3. Here's what Joe shows to Theo. Theo, I see the two indexes we talked about, books by ISBN and authors by ID. How do you differentiate a record from an index in DOP? Joe, in an entity diagram, there's a clear distinction between records and indexes. But in our code, both are plain data. Theo, I guess that's why this approach is called data-oriented programming. Joe, see how straightforward it is to visualize any part of the system data inside a program? The reason is that data is represented as data. Tip: in DOP, data is represented as data. Theo, that sounds like a lapalisade. Footnote 1. A lapalisade is an obvious truth, a truism or tautology that produces a comical effect. Joe, oh, does it? I'm not so sure. In OOP, data is usually represented by objects, which makes it more challenging to visualize data inside a program. Tip: in DOP, we can visualize any part of the system data. Theo, how would you retrieve the title of a specific book from the catalog data? Joe, great question. In fact, in a DOP system, every piece of information has an information path from which we can retrieve the information. Theo, information path? Joe, for example, the information path to the title of the Watchmen book in the catalog is this, in brackets. Theo, I see. So, is an information path sort of like a file path, but that names in an information path correspond to nested entities? Joe, you're exactly right. And once we have the path of a piece of information, we can retrieve the information with Lodash's _.get function. Joe types a few characters on Theo's laptop. Theo is amazed at how little code is needed to get the book title. Theo, neat. I wonder how hard it would be to implement a function like _.get myself. After a few minutes of trial and error, Theo is able to produce his implementation. He shows Joe the code. After testing Theo's implementation of get, Joe compliments Theo. He's grateful that Theo is catching on so quickly. Joe, well done. Theo, I wonder if a function like _.get works smoothly in a statically typed language like Java. Joe, it depends on whether you only need to pass the value around or to access the value concretely. Theo, I don't follow. Joe, imagine that once you get the title of a book, you want to convert the string into an uppercase string. You need to do a static cast to string, right? Here, let me show you an example that casts a field value to a string. Then we can manipulate it as a string. Theo, that makes sense. The values of the map are different types, so the compiler declares it as a map of string and object. The information of the type of the field is lost. Joe, it's a bit annoying, but quite often our code just passes the data around. In that case, we don't have to deal with static casting. Moreover, in a language like C#, when using the dynamic data type, typecasting can be avoided. Footnote 2. See this link for the C# documentation on the built-in reference to dynamic types. Footnote 3. See Appendix A for details about dynamic fields and typecasting in C#. Tip. In statically typed languages, we sometimes need to statically cast the field values. Theo, what about performance? Joe, in most programming languages, maps are quite efficient. Accessing a field in a map is slightly slower than accessing a class member. Usually it's not significant. Tip. There's no significant performance hit for accessing a field in a map instead of as a class member. Theo, let's get back to this idea of information path. It works in OOP too. I could access the title of the Watchman book with this. I'd use class members for record fields and strings for index keys. Joe, there's a fundamental difference though. When records are represented as maps, the information can be retrieved via its information path using a generic function like _.get. But when records are represented as objects, you need to write specific code for each type of information path. Theo, what do you mean by specific code? What's specific in this? Joe, in a statically typed language like Java, you'd need to import the class definitions for catalog and book. Theo, and in a dynamically typed language like JavaScript? Joe, even in JavaScript, when you represent records with objects instantiated from classes, you can't easily write a function that receives a path as an argument and display the information that corresponds to this path. You would have to write specific code for each kind of path. You'd access class members with dot notation and map fields with bracket notation. Theo, would you say that in DOP the information path is a first-class citizen?